So, and a lot of the talks today, this week, have been about endpoint, either the sources or the targets of attacks or securing things. Where we live, and that this talk is about the core of the internet, how traffic moves from across the core of the internet, and it's an area that we work with a lot, and it's something I'm going to talk about in this talk here. So who are we? So we were Renesys, if you had heard that name before. So we Renesys. I've been with Renesys for over 5 years, and typically we work with large telecoms. So we work with providing them competitive business intelligence that's derived algorithmically from routing data, performance data on how their traffic is moving around the internet. And we're often in the news. So we were in the news recently when North Korea went down. We were the source for that. When the submarine cable comes active in either Cuba or Crimea, then we're the ones kind of keeping an eye on significant changes to the global infrastructure of the global internet. So we were acquired last year by Dyn. This is Dyn. You may know Dyn DNS. That's the company, and so we are helping them with their offerings for internet performance stuff, trying to use the knowledge that we've got to help improve their offerings for traffic management. So this was formerly a Renesys slide, now it's a Dyn slide, the Dyn measurement infrastructure. So we have live feeds from about 400 telecoms around the world of their BGP data. On top of that, we overlay basically a global traceroute infrastructure. We have about 170 servers around the world that are doing traceroutes to basically the entire internet. We generate about 250 million trace routes a day. Those are within a couple minutes brought into our data centers and processed into our tools. And so we have a pretty good sense for when there's changes of traffic at the core and why those occurred. So this has been mentioned at a previous talk here, but just as a recap for BGP. So we have about 49,000 autonomous systems that represents all the routing on the internet. An autonomous system is some sort of entity that speaks BGP, that handles routing for traffic. And that can be either an ISP or an enterprise, but it's a single unit of entity in the BGP realm. Each AS will advertise its address space, and then those routes will then be carried on to their transit providers and peers. And each AS independently selects best path based off of most specific first, then shortest path, and then on top of that, there's local preference. Typically, whatever is the cheapest transit provider is often chosen, overriding some of these other rules. However, despite the efforts to bring cryptography into routing using things like RPKI, the present state is that any AS can announce any other AS's address space or any address space that isn't being used. And there's I'll talk about a couple examples of that. So Costin actually this morning mentioned this piece of research we did about 1.5 years ago, where we were identifying an entity in Belarus redirecting traffic, basically hijacking routes for first U.S. financial firms, and then going on to foreign governments, and doing it in a way that the route propagation was curtailed, so that there was a clean path out that the traffic could make it to its final destination. So people who were affected, unless they realized there was a higher latency, they may not have noticed much of a difference. Meanwhile, their traffic is getting rerouted through Belarus. We saw this both in the routing, and then we could test this by watching a trace route get sucked into Belarus and come out the other side, make it onto its final destination. Let's see, in the last year, we saw the Bitcoin BGP attacks. So this is Dell SecureWorks came out and broke this story. These graphs, actually, we had discussed this with Amazon the following day. These are graphs generated in our discussion. We had seen the routing activity, but I didn't know enough about Bitcoin to figure out how one could make money off of hijacking routes containing Bitcoin domains. I know now, but good on them for putting that together. But so there's another class of traffic redirection that occurs much more regularly that isn't necessarily a an attack. This is just a normal course of doing business between ISPs. There's a lot of redirection going on where people are making errors and traffic gets shifted in great distances. And so let me explain what this is. Something we've been trying to talk about in the last, say, 6 months or so, because we see it in our data a lot, and we have to interact with ISPs about this. So when two ISPs peer, basically they are doing this as a cost-saving measure. So they're trying to not send traffic to their transit providers. They're making a direct connection to each other, and they're just going to share traffic between the cones, the customer cones of their corresponding networks. And so the little graphic is showing, the announcements should go from, so A and B are, ISPs A and B are peering. Announcements go from A to B and go down into B's cone. Then the traffic would follow the path the opposite direction, where the traffic would come out of B's cone and go into A. And that's how it's supposed to work. And there's a couple ways this gets messed up, and it happens pretty regularly. All right, so routing leak scenario 1 is where B, instead of sending the routes just to its own, into its own cone, sends the routes either to its providers or its peers. The end result is that traffic from anybody receiving those routes in the outside world will now go through B to get to A. And so on the inbound traffic to A's customer cone, B is inserted inadvertently. The opposite is true as well, where for the routes that B is getting, if it's sending those onto routes that it's receiving from its providers and peers, if it sends those onto A, and A will send those to its customer cone, then traffic will then be sent through B to get to outside. So outbound traffic will now go through B. So let me give you a couple examples of this. So the kind of the biggest, most interesting one we had come across in the last year was VimpelCom and China Telecom. So VimpelCom is one of the big three wireless carriers. There's three big wireless carriers in Russia. And they, about a year and a half ago, made a big announcement how they were signing a network sharing deal with China Telecom, which is actually a very common thing. There are a lot of Russian large networks that are setting up deals in the Far East to try to use some trans-Siberian connectivity to be able to offer back to the Far East low latency paths to Europe. And so this is not so remarkable that this connection would be made. However, on about a dozen different instances in the course of 2014, we saw China Telecom messing up the routing for VimpelCom and basically inserting itself into the path of traffic, both inbound to VimpelCom and outbound. And we saw this from routing within both of the cones of these networks. So the example, it's a little hard to read here, but this is an example trace route out of one of our servers in Moscow, getting redirected through Shanghai, then to LA. This is en route to Fairpoint, our local crappy provider in New Hampshire. Normally this would have gone across Europe and across the Atlantic instead of going through the Pacific. That's an example of outbound traffic getting impacted by this routing leak. And then there's an example of, is it going? Inbound traffic. You can see these charts are latency charts. This is, we come at this from a perspective of trying to understand performance, and there's a performance hit when traffic is redirected through China, both geographically and as well also because China has some chronically underprovisioned international links for various reasons. And so if you're going to pull traffic through the molasses of China, you're going to take a latency hit. And so in each of these examples, we have Reston, Honolulu, San Jose, Guadalajara as the provider that was traversed to get to VimpelCom changes to China Telecom, then there's a spike in the latencies. Another example, another type of peering link that can go wrong is a CDN link. So CDNs also peer a lot, not for quite the same reasons as ISPs, but they also want to make their connections to. So Google has thousands of peers, and it's in their interest to peer and get traffic directly to ISPs so they can serve their customer base. And so, but every one of those ISPs has the power to mess up then the CDN. And so in this case, we had Vocus out of Australia. November was leaking routes from Microsoft, and it was a condition that had persisted for about 6 days. And what was kind of wild was if you were an ISP or downstream of an ISP that peered with Vocus in Los Angeles, then you would see something like this, where these are screenshots from one of our products, Dyn Internet Intelligence. We see traffic from San Jose, California to Redmond, Washington, normally is about 30 milliseconds to get from one place to another, spikes up to almost 200 as it's having to hairpin through Australia. And so when you break out the path view of how this is happening, it's going from California, Vocus, Australia, and to Redmond, Washington. And so that's a suboptimal routing path. And this one also is not an attack. I don't want anybody to think this is an attack, 'cause in fact, we were in discussion with both of these companies, and there was an error that caused this to take place. But this is kind of par for the course. There are these routing leaks that are occurring that are shifting traffic great distances. And to be very, very honest, if one of these showed up and I didn't have the ability to reach out to the network operators to find out what happened, I'm not sure I would be able to tell the difference between something malicious and something benign, because there's so many of these benign examples. Speaking of things that aren't benign, so last month I wrote a blog about when you work with routing data a lot, you come across a lot of, we'll call it fraudulent routing, routing that's done for some sort of ill purpose. And I wanted to just document 6 different cases of different parties around the internet doing IP squatting, basically announcing address space they don't own, either temporarily or for long periods of time, to do a set of different things. And this technique's long been known for to generate spam, so you can just generate a lot of spam. If your IPs get blocked, you just release it and move on to somebody else's address space, start sending spam out. There's also documentation of this being a technique for distribution of malware, of botnet CNC. The objective, or the benefit of doing this kind of thing is that the perpetrator gets to obfuscate its true source, and that's another point I would make to this crowd, to this conference of security analysts, is that the IP address you see in your log may or may not be where you thought it was from. And so we saw like Comcast address space was getting hijacked by one of these parties last fall. And so during that time, if you were getting hit with something from Comcast address space and it showed up as New Jersey Comcast, it was actually getting routed out of Eastern Europe at that time. And so this attribution based off of IP addresses, I'm not saying it can't be done, but just proceed with caution. It's knowable, but it requires some. I've got the ability to do retrospective BGP analysis, but the average security analyst doesn't necessarily have that ability at their fingertips. And so. Let's see, in this blog, we kind of went through a handful of different cases. In this first one is out of St. Petersburg, where just about every hour they announce different address space of a different, most of it's unused, sometimes they hijack space. They're doing different stuff at that time, and it's been going since June. In fact, it's going right now as we speak. And what that's used for, I'm not quite sure, but anything that was getting caught in anybody's logs from that entity is guaranteed to not be marked as a party from St. Petersburg. In that case, they also do their routes through 2 levels of ASs that are also unused ASs, so it makes it fairly hard to track. For us, we follow transit patterns because that's what we've been doing for telecoms for a long time, and so that's where it sticks out to us. We see the St. Petersburg Internet network show up as a provider in Taiwan, and then it's in Australia, and then it's in Russia, not Russia, but somewhere else. The next one down is out of Portugal, and these guys just nail up their IP squatting for days on end. This last example we talked about in the blog, it was maybe a slight advancement in this space, where we saw a party also in Russia that was using unused address space, but then also primarily unused, using plausible ASs to originate the address space. So they were using, we used 3300, but also 5400 is the main AS for British Telecom. So it would announce British Telecom's unused address space with an AS origin of British Telecom, and then route it through Ufa, Russia, where I had to go look up where that is, and so that's that. If you were just doing a simple mapping of what was the origin of the IP address at the time, it would show up as what would be plausible, a plausible legit. You would need to know the transit pattern was off, and have to be highlighted in that. So this makes things like doing AS reputation. I think this is a big complication for that. Again, I'm not saying it can't be done, but I had other examples in that blog of just other cases where cable and wireless was falsely the origin of bad routes. You wouldn't want to block out what is now Vodafone from your if you were to block traffic from an AS that you've listed as having a bad reputation if that was based off of some of these false AS origins. Let's see. So, in summary for this, I kind of just wanted to highlight a few different issues that we brought up in the security area. So, I think anybody familiar with the space has known for a long time that global internet routing is vulnerable to manipulation. Hijacking routing errors are causing misdirecting traffic. This is happening quite frequently. The fraudulent BGP routing is occurring at a near constant pace. It's happening all the time. And so therefore I would caution the security analyst community to exercise caution on attribution based off of IP addresses and reputation based off of ASNs, because it's, I think we can say it's not so simple as maybe some may believe. And then we would try to make the argument with the routing leaks that enterprises and ISPs would do well to monitor their routes, both the ones that both their own routes that they're sending out, but also the ones that of their peers and their parties that they do a lot of business with, because there's a lot of incidents going on in this space. With that, I'll take any questions.
Plenty of time.
Yep.
How do you think these routes and BGP or not? Because I know a lot of data centers I've worked with, their DR sites are all BGP based to auto fail over and whatnot. That would totally get messed up. But what about all the CDNs that have centers all over the world trying to get traffic to a specific spot? I would think that it would just mess their stuff all up.
Let's see. So, as far as them sending traffic, so there's with CDNs. So there's a couple of techniques that they use for offering up. So there's some Anycast out there. Like Cloudflare is probably the biggest party out there that does Anycast, and they broadcast it as part of their advertising. Akamai, on the other hand, does very little Anycasting. It does all the traffic management through DNS, and so Cloudflare's had, actually both Cloudflare and Akamai have had routing leaks impact their networks. So as far as the side of them hosting stuff, that they are vulnerable, where if they're peering with a party that an ISP that makes a mistake, like Cloudflare had a leak with Internexa out of South America. Those guys could by making a mistake, impact their network. I think they caught that pretty quick, and so that's the best you can hope for. But it's a vulnerability for sure.
Other questions? Thank you, Doug.
All right, thanks.